Welcome to Study Loop.
Okay, let's just begin solving the problem 20. The physics picture of this problem is two slits diffraction. We have two slits, and the slit width is A. This is also A, and their distance between is D equals 3 times A. And we also have a screen. It's relatively far away from those slits. The question is this: if we have a light wavelength lambda, for the very beginning, if we didn't consider the diffraction, we just consider there are two slits and the light goes through those two slits and the interference happened. What is the maxima position on the screen? It's easy because we learned that it happened when the sine theta equals I times lambda over d here. We may realize that if we suppose this is a central maximum, it will, the secondary and the third maxima will appear aside the central maximum, and it's periodically. Okay, so like this. And if we draw the plot, it will be something like this. Central maximum, then secondary, and third. This is the other side. This is part A, or say the answer to the part A of this problem. And the second, or say the part B of this problem is, if now we begin include the diffraction effect, what will be the intensity of light on this screen there? So we have the formula 36.5. I equals I0 times sine beta over 2 divided by beta over 2, then we square. And at the central maximum, we have the intensity of light equals I0. So that's the question, and this is the result. And we also have beta equals 2 pi sine theta times A over lambda here. If we plug in d equals 3a, beta equals 2 pi sine theta times d over 3 times the wavelength lambda there. For the, okay, so this is B here, and this is A. And the part A asks what will be the next four maximum. We will learn that one m equals 1, 2, 3, 4. We tentatively didn't consider the minus 1 or -2, -3, -4 because they are just symmetric to those results. So if we in the part C, we asked about what kinds of those maximum will miss. This is about the thing what we want to consider the diffraction and the interference together. Actually, we just want some place the interference maximum at the intensity of light from diffraction together. We just plug in all those theta values. Remember, a different m value will give us different sine theta. We just plug in those sine theta here, and we will find some result. For example, if we have missing maximum, the I should be 0. So this is something square, so it should be equal 0 or bigger than 0. So the sine beta over 2 must be 0. So we just plug in all those 4 possible values to this and try to figure out which value will give our 0 sine value here. If sine beta over 2 equals 0, beta over 2 should be n times pi, and n equals 1, 2, 3. It's whatever. It's just positive integers. And finally, what we find, we have 4 possible values for sine theta, and they are lambda over d, or lambda over 2d, or lambda over 3d, or lambda over 4d. What we found is lambda over 3d, if we plug it into the equation of beta, it will give us, how much is it? It will give us the, how much is it? It is just 3D. It will be the, oh, I'm sorry. It's not. There's something wrong there. It's 2 lambda over d, 3 lambda d, 4 lambda over d. If we plug it into here, what do we get? Beta equals 2 pi. And this will give us beta over 2 equals pi. There will be pi. And the sine pi equals 0. And our intensity of light is 0 at the theta equals arc sine. Here. So this is what we find. So what's the difference compared with the picture in chapter 36, the picture 36 on the top. It's this. As to the example from the textbook, for every fourth interference maximum at the size on the screen, it will be missing. Like m equals plus minus 4 plus minus 8 plus minus 12, etc. like this. But for our case, we will have every third maximum at the side will be missing. So the m equals plus minus 3, plus minus 6, plus minus 9, something like that. So whatever, this is actually the interference effect with the diffraction effect together. That's what we calculated